All right, welcome everyone to our fourth and final International System Safety Workshop. I'm John Sloan with the U.S. Federal Aviation Administration's Office of Commercial Space Transportation. And as a reminder, as we go through the presentations today, you can type any questions that you have into the chat feature, and then we'll get to those as we go. And today's speakers are Sean and Kenyatta. And if our charts are ready, Sean, over to you.
Hi, everyone. I'll be presenting the Computing System Safety Regulations under Part 450.141. Next chart. In prior sessions, we have discussed 450.103, System Safety, 450.107, Hazard Control Strategies, 450.109, Flight Hazard Analysis, 450.143, Safety Critical Design Requirements, 450.141, which is what I'll be speaking to today, Computing System Safety Requirements. Next chart. Next chart. So this diagram shows how the Computing System Safety Regulation 450.141 interfaces with system safety regulations we've been discussing in prior sessions. As we will discuss when we get to 450.141A, any software or data used to implement potentially hazardous functions or mitigate public safety hazards are considered computing system safety items, which I'll use the term CSSIs, under Part 450. The 450.107 hazard control or functional hazard analysis is a critical step that identifies and assesses the criticality of CSSIs. The functional hazard analysis should note how each function is implemented: hardware, software, firmware, discrete logic. Any software, firmware, discrete logic implementing a function whose failure could present a public safety hazard is automatically a CSSI. For components that include CSSIs, the functional hazard analysis should assess the CSSI's degree of control and level of criticality using an appropriate method. As we'll see, the functional hazard analysis is not the only means by which CSSIs may be identified. Other types of analyses and the applicant selected hazard control strategies, 450.107 through 111, also play an important role. Together, the criticality assessment determines what development and testing activities are required for each CSSI. That's the rules mechanism for setting the minimum level of rigor by criticality. Specifically, CSSI criticality assessments scale the expected level of rigor for documenting CSSI descriptions, requirements, development processes, and verification and validation evidence. Next chart. The AC is structured after the rule and provides examples of the types of evidence required by the rule for safety requirements, development processes, V&V evidence. Each subpart of the regulation has one or more documented means of compliance in the AC. The AC is also designed from the perspective that computing system safety is a process, not an event. Good processes must be established and followed throughout the development lifecycle to ensure the production of safe CSSIs. There are several appendices in the AC that are also worth noting. A provides a subset of software safety requirements. The subset of requirements in Appendix A includes functional, performance, and process requirements adapted from a wide variety of government and industry sources. B provides some sample safety analysis methods, including software failure modes and effect analysis, and software fault tree analysis. Appendix C and Appendix D provide lessons learned in software safety from the spacecraft and aircraft industry. Next chart. The AC documents two distinct acceptable means of compliance. The first is especially important for autonomous flight safety systems. It is a tailoring of RCC 319 Appendix A. This means of compliance is typically used in conjunction with a highly reliable flight safety system developed in accordance with 450.145 to implement a 450.108 hazard control strategy. Applicants pursuing this means of compliance should perform tailoring during the pre-application consultation. An AFSS is usually, software on an AFSS is usually the highest criticality CSSI on a vehicle that uses them. The other method of compliance is compliance with the rule directly. This means of compliance is broader and is generally applied to other CSSIs, like software used on flight computers or other avionics components, even ground systems. Applicants using this means of compliance should identify CSSIs and assess their criticalities during pre-application consultation. Notably, these are available means of compliance in the AC, but they may not be the only means of compliance that are considered. Next. .141A gives the more formal definition of a CSSI. Any software or data that implements a capability that by intended operation, unintended operation, or non-operation can present a hazard to the public. To comply with this regulation, the applicant must identify all CSSIs. To comply with 450.141A2, the applicant must assess the level of criticality of all CSSIs based on their level of control over hazards and the severity of those hazards. Specific assessment methods are not prescribed by the regulation. The applicant is allowed to define a categorization or assessment scheme that best suits their operation. Several accepted methods are provided in AC 450.141.1A. It's also important to know that 141A ends up being the interface with the system safety process we've been describing in previous sessions. The assessments produced by compliance with 141A also scale the minimum level of rigor for compliance with all the subsequent requirements in 141. This is how the regulation accomplishes the goal of scalability without prescribing a specific scale to use. Next chart. In practice, 141A requires the identification of software data that has a potential role in endangering or protecting the public. All such software or data are CSSIs. This includes software that could interfere with the operation of other CSSIs or CSSIs involved with hardware and human interfaces. It is an intentionally broad term meant to capture all such software or data that has a public safety role in a given operation. Part of pre-application consultation is the identification of CSSIs and reviewing them with the FAA. Early agreement on a list of CSSIs and their criticality helps scope the license evaluation and give the applicant a clearer path to licensing. It's also important to identify high criticality CSSIs early because they can be subject to very rigorous development processes and, as we'll see, V&V requirements. Next chart. Identification of CSSIs is an extremely important step in the process of demonstrating compliance with 450.141. As discussed earlier, a CSSI is a collection of software data that can present a hazard to the public by some mechanism. They become evident as a cause or mitigation of a hazard. They may be identified in the functional hazard analysis. That's the place they are most often identified. They may be identified by other system safety analyses. For example, CSSIs can show up as software used to implement mitigations identified in the 450.109 flight hazard analysis. Lastly, they can also appear as part of implementing a hazard control strategy. A really prominent example is AFSS software that's used as part of implementing a 450.108 hazard control strategy. Next chart, please. Now, the criticality assessments are required to consider two distinct factors: severity, which characterizes the magnitude of consequence arising from a potential hazard. That's the term catastrophic, critical, etc. In general, the FAA considers all public safety hazards to be catastrophic. CSSI criticality increases as severity increases. The second factor is a little more nuanced, and that's degree of control. Degree of control characterizes a CSSI's role in a hazard in terms of its control authority. Again, CSSI criticality increases as degree of control increases. As a more concrete example, a piece of software that automatically takes action to protect the public, such as an AFSS terminating a vehicle, has a much higher degree of control than software that has a human in the loop. There are several methods of assessing criticality defined in the AC. Many of them are derived from existing sources like MIL Standard 882E and DO 178C. These criticality assessments drive the minimum level of rigor for development and verification and validation of all CSSIs. One important note that the FAA has clarified since the adoption of 450 is that a 145 highly reliable flight safety system can effectively reduce the degree of control of all non-AFSS CSSIs. This is because the flight safety system can intervene with high reliability to prevent safety hazards arising due to the failure of other CSSIs. This essentially acts like an additional level of fault tolerance for hazards for which the FSS provides protection. Using the 882E degrees of control, which is one of the methods in the AC that's approved for assessing criticality, flight computer software on a vehicle without a 145 FSS has an autonomous degree of control over hazards. With a 145 FSS, the flight computer software can be seen to have a redundant fault-tolerant degree of control. Thus, the level of rigor required on the flight computer software processes can be lowered. Now, that doesn't mean that because you have an FSS, you do not have any other CSSIs. You most likely will have other CSSIs, like the aforementioned flight computer. Their failures may be mitigated by the FSS, but the applicant is still required to do that analysis. You may have two different means of compliance. You may have AFSS software that you demonstrate compliance using 319. You may have other CSSIs that you have to submit direct evidence to show compliance in accordance with the other means of compliance in the AC. (141B) starts to get into what we do with these computing system safety items once they have been identified. It requires the applicant to develop safety requirements for all identified CSSIs. A safety requirement is a computing system requirement that specifies an attribute or functionality that affects public safety. It's a term that allows us to separate requirements for, say, user interface color choices or cosmetic details from safety requirements for things like fault detection and recovery. This is another aspect of the rule that's meant to help scope the applicant's submittal to exactly what is public safety related. And we'll discuss each of the 4 requirements in 141B in subsequent slides. Next chart. Now, B1 requires a process for identifying and evaluating CSSI safety requirements that is consistent with their criticality. B2 requires the operator to have processes to ensure that safety requirements are complete and correct. B3 requires that all safety requirements be implemented. Now, this is typically met by submitting evidence of execution of the development process that is compliant with 141C. B4 requires V&V of the implementation of safety requirements. In practice, this usually means testing of all safety requirements. Notably, it includes a requirement for independent testing of all CSSIs that are deemed to be safety critical with respect to 450.107. This mirrors the way 450.143 is invoked for when safety critical hardware systems are identified. Generally, the independent test requirement is met using an independent verification validation project, aka an IV&V. Now, 450 does not prescribe any specific IV&V requirements. Independent itself is discussed in the preamble to the final rule. For AFSS specifically, IV&V requirements can be found in RCC 319 Appendix A. I'm going to hold here for questions. This one usually has some. Okay, no questions. Keep moving. Back to safety requirements. Safety requirements in this context are a subset of all of the system requirements for a CSSI that have public safety consequences. They define or describe safety-related design attributes, performance, or functionality. The expectation is that the applicant's requirements management process has a feedback loop that serves to identify new safety requirements as needed during the lifetime of the program. We require that safety requirements are evaluated for completeness and correctness. Similarly, this is normally accomplished with a cyclical process that involves internal review cycles. When looking at a requirements management process, we really look to see that the applicant identifies what their system needs to do, evaluates why their system needs to do it, implements, i.e. defines how their system will do it, and describes the means by which they will verify that the system can do it or actually doesn't. Safety requirements should be implemented using a software development process that meets the requirements of 450-141C. Verification and validation strategies under B4 should be deployed selectively based on criticality. Testing is preferred when feasible, but other verification methods such as inspection and analysis may be considered. For CSSIs where an IV&V is required, it should be managed independently of the development process. The IV&V team should have incentives that encourage thoroughness. Schedule and throughput should not be the only metrics. The IV&V team should have the latitude to check for undocumented requirements because there may be working assumptions that the developer was not aware of during the design and implementation of the software. Finally, the IV&V should provide feedback and findings to the developer in a timely manner and track them to closure. Next chart. So now we're getting into 141C. 141C defines the development process requirements. These requirements are meant to set expectations regarding an acceptable CSSI development process. Operators do not need a separate process for each CSSI, but the development process selected must be appropriate for the level of criticality for each CSSI. It's not uncommon to have tiered software development processes that apply different levels of verification and validation, code review, depending on the criticality of each CSSI. Each requirement from 141C will be discussed in subsequent slides. In practice, the applicant must define a software development process that meets all requirements in 141C. This process may be made up of development procedures, coding standards, or anything else that goes into producing code within their organization. These requirements are intentionally performance-based so they can scale with criticality. The requirements themselves at a high level are assignments of responsibility for development tasks, usually by position or title, review processes for requirements vetting, implementation, and testing, process involved using safety critical code appropriately trained. Trace safety requirements to verification and validation evidence. Process that allow the operator to test the content of the software used in each proposed operation. Verification and validation processes proportional to criticality. Reuse and third-party policies that ensure all safety requirements are verified. Means of compliance for each of these can be found in Section 8 of 450.141A1. For assignment of responsibilities for safety tasks, these are usually by position or qualifications. Safety task is a catch-all term here that may include design, code implementation, code reviews, testing, or anything else called out in the applicant's software development process. This requirement is met when the applicant documents who should perform every task identified in the software development process. Review and approval processes are similar to and often include code review. They can also include larger design review meetings like CDR, PDR, etc. They can also include the types of reviews normally performed by IV&V assessors, like requirements reviews. This term is intentionally flexible to allow for different methods of meeting the requirement. The key here is that more than just the developer is involved in the review, and there is a feedback mechanism built into the process that ensures all review comments are addressed. This requirement is met when reviews are documented that are sufficiently rigorous for the CSSI's assessed level of criticality. Note, depending on the CSSI's criticality, there may be multiple layers of review built into the process. It's not uncommon to have both high-level design reviews and low-level code reviews. Training processes or qualification processes, back to the preview. Yep. Training processes or qualification processes should result in putting appropriately trained and experienced personnel in safety roles. This part of the reg is highly applicant specific, but our evaluation focuses on verifying that the applicant has sound standards and methods for getting the right personnel in place to execute safety tasks. Continuing with 141C, the next requirement is to define processes that trace requirements to verification and validation evidence. This connects the CSSI safety requirements from 141B and demonstrates that each has been implemented. Our evaluation here focuses on any potential errors or gaps in traceability between requirements and verification evidence. For configuration management, we look for a process that is sufficient to specify the content of each released version. CM is a much larger discipline than that, but this is the minimum performance standard for this part of the rule. For CSSIs used aboard the vehicle, this process should also cover how they are loaded and how the correct version of each CSSI has been confirmed to be loaded. Verification and validation under C6 should be in proportion to criticality. Meeting this requirement often involves the submission of test plans, test results, reports, or other supporting analyses like inspection activities. Next chart. The last of the 141C requirements are related to previously developed CSSIs. These could be reused or from a third party. We give broad latitude for defining policies for reused and third-party CSSIs because there is such a wide variety of such tools used in industry. What we're primarily looking for from these policies is verification of any safety requirement imposed on third-party or reused CSSIs. Ideally, these policies should ensure that previously developed CSSIs are treated just like newly developed CSSIs. For reuse CSSIs, there should be a step that evaluates the differences between prior uses of the CSSI and uses in the newer system. This may take the form of a system-specific software hazard analysis. For third-party CSSIs, the applicant does not necessarily need to replicate tests or analyses conducted by the supplier. Instead, when it's available, they should pull that data into their own safety analyses. But for highly critical third-party CSSIs, specific tests or analyses that verify that all safety requirements are met may be needed. Again, these requirements are meant to cover commercial off-the-shelf, government off-the-shelf, legacy, or software adapted from prior systems by the operator. Oh, jumped ahead of me. No worries. The last part of the advisory circular I'm going to talk about, section 8.3, doesn't relate to a specific 141 requirement. Instead, it provides a set of processes and practices that support the accomplishment of other development process requirements. This is intended to be a set of tools, notes, and concepts that may help in accomplishing the goal of safe software development. This includes things like software implementation analyses, development standards, quality assurance processes, formal inspections, anomaly reporting, which is part of establishing some of the feedback loops we discussed earlier. It also can cover maintenance of hardware, maintenance of software, and good practices for building maintainable software, like partitioning. Sure. (141D) covers the computing system application requirements. This includes everything the applicant must submit to demonstrate compliance with 141 as part of their 450 license application. These requirements relate directly to the previously discussed requirements. Next chart. What 141D does generally is require documentation substantiating compliance with subparts A through C. It requires a list of CSSIs and their criticality assessments in accordance with Part A. It requires safety requirements for each CSSI in accordance with Part B. It requires the development process in accordance with Part C. In addition, it requires evidence of execution of the development process. That is to say that each CSSI has documentation showing that it has completed the development process. This is generally met by providing soft development process artifacts, such as requirements documentation, design documentation, test plan, code review artifacts, software hazard analyses, be a bunch of stuff. Finally, it requires evidence of implementation of all safety requirements. Generally, this is met using that requirements to traceability process documented as part of 141C to link all of the safety requirements submitted to verification and validation evidence. Next chart. Next chart. The identification of CSSIs is meant to mirror the identification of safety critical systems under 143. There is a system whose function can contribute to or mitigate a public safety hazard, and it has software data aspects, then it is a CSSI with respect to 450.141A1. That is not necessarily limited to vehicle software. Ground support equipment and even analysis software can have an important role in protecting the public. The important thing to keep
Oh, I think we lost Sean's audio right at the end, but I think he was about done.
I'll check.
Okay, you're coming back slowly, Sean, but why don't we go to any questions for Sean? Or do we have any questions in the chat? I don't see any. And no, Kenyatta. Kenyatta, are you ready? Why don't we go to the next slide and start the next section?
Thank you, John. So thank you all for attending the last session of the International System Safety Workshop. I will discuss requirements and expectations for Code of Federal Regulation 450.139 toxic hazards for flight. As a caveat, the advisory circular for toxic hazard mitigation 450.139-1 is in the final stage of review prior to publishing. So this session is designed to encourage dialogue concerning toxics. Next slide. For toxic hazards for flight applicability, this section applies to any launch or re-entry vehicle, including all vehicle components and payload, which use toxic propellants or other toxic chemicals. In addition, no toxic release hazard analysis is required for kerosene-based fuels unless the administrator determines that an analysis is required to protect public safety. And again, as a reminder, the Toxics AC is under development and is forthcoming to provide acceptable means of compliance for 450.139 toxic hazards for flight. Next slide. Generally speaking, an operator must conduct a toxic release hazard analysis in accordance with paragraph C of this section. An operator must also calculate or manage risk of casualties that may arise from exposure to potential toxic release. And the operator must perform a toxic risk assessment to ensure public safety. Within these steps, it is expected that an operator would conduct and present detailed analysis, and depending on those results, the operator should demonstrate, document, and implement toxic containment or any mitigations necessary to prove any member of the public are removed from a defined hazard area. Next slide. A toxic release hazard analysis should account for any data needed to determine if the public is protected from any possible toxic release that could occur during a nominal or non-nominal flight, launch, or reentry ground operations. The analysis must include a worst-case release scenario analysis or maximum credible release scenario for each process that involves a toxic propellant or chemical. Finally, the data submitted should include the following: vehicle parameters and source data, propellant types, propellant quantities, combustion thermodynamic data, phase changes of propellants and the derivatives of those propellants, population counts, structure vulnerability, exposure response function and location, weather predictions, and any operational constraints and emergency procedures that provide protection from toxic release. Next slide. To demonstrate toxic containment, an operator using toxic containment must manage the risk of any casualty from the exposure to toxic release by one of two things. Number one, evacuating or being prepared to evacuate the public from any toxic hazard area in the event of a worst-case release or maximum credible release scenario. Or number two, employing weather constraints to limit an operation to time during which prevailing winds or other conditions ensure that any member of the public would not be exposed to toxic concentrations greater than those accepted toxic thresholds for acute casualty in the event of a worst-case release. Please note, you can refer to the U.S. Environmental Protection Agency, EPA, acute exposure guideline levels, and we call those AGLEs, for appropriate concentrations or threshold levels for any toxic propellants. AGLEs set levels of chemical concentrations that pose a defined level of risk to humans. These levels are used in preventing and responding to any type of disaster. Next slide. According to 450.139E, toxic risk assessment, an operator using toxic risk assessment must establish flight commit criteria that demonstrate compliance with the safety criteria of 450.101 safety criteria, including launch risk criteria, collective risk, individual risk, aircraft risk, and each of the impacts. The FAA expects a toxic risk assessment to include airborne concentrations and duration thresholds of toxic propellants or other chemicals such as dose response, peak concentrations of exposure to toxic release. We also expect the toxic release risk assessment to account for any physical phenomena expected to influence any toxic concentration in the area surrounding the potential release site. And finally, it should include hazard area identification, including the population or receptor locations. Next slide. In continuation, the toxic risk assessment should account for all members of the public who may be exposed to the toxic release. This should cover public on land or on any waterborne vessel, populated offshore structures, and aircraft that are not directly involved in the licensed launch or reentry operation. Again, the public that we're protecting includes the public on land, any waterborne vessel, populated offshore structures, or aircraft that are not directly involved in the licensed launch or reentry operation. And finally, the toxic risk assessment should account for any risk mitigation measures applied in the risk assessment, such as risk characterization or mitigations, or even the evacuation plans. Next slide. Application requirements. In order to demonstrate compliance to 450.139 toxic hazards for flight, an applicant must submit the following requirements that are listed. I will take time to read these because they're important in this application requirement. So number one is the identity of toxic propellants, chemicals or combustion products or derivatives, and the possible toxic release. So basically, an applicant would take time to identify all of the commodities on board and include those, and present them to the FAA so that we can actually identify those toxic propellants. Number two, the applicant's selected airborne toxic concentrations and duration thresholds. And again, I mentioned the AGO level, so referring to the EPA toxic concentration so that you can know those parameters for each of those propellants that are on board. The meteorological conditions for the atmospheric transportation and buoyant cloud rise of any toxic release from its source to downwind receptor locations. The application should also include characterization of the terrain as input for modeling the atmospheric transport of a toxic release from its source to downwind receptor location. So basically, whichever dispersion modeling tool that an applicant chooses to use, they would use that and input weather parameters, recent and current weather parameters that will allow modeling of such activity, including downwind receptor locations or buoyant cloud rises or things like that. And the application should also include the identity of toxic dispersion model used. For example, the FAA does not solicit the use of any specific tools, but there are tools that are available to do toxic dispersion modeling. One to name is Aloha. And there are several others out there that are available for applicants. And the next step in the application requirement includes representative results of the applicant's toxic dispersion modeling to predict concentrations and durations at selected downwind receptor locations to determine the toxic hazard area for a released quantity of the toxic substance. Next slide. The application requirements also include a toxic release hazard analysis, including, I mentioned that before, but it also includes a description of the failure modes and associated relative probabilities for potential toxic release scenarios used in the risk evaluation, and the methodology and representative results of an applicant's determination for the worst case or maximum credible quantity of any toxic release that may occur during the operation. And the last application requirement that we're looking for and are expecting, according to 45139B2, is a toxic containment in accordance with paragraph D of this section. We need the applicants to identify evacuation plans, weather constraints associated with launch commit criteria needed to ensure that the public will not be within a toxic hazard area in the event of a worst case release or maximum credible release scenario, or a toxic risk assessment in accordance with paragraph E of this section to demonstrate the safety criteria as previously mentioned from 450.101 will be met. And the population characteristics and receptor locations that are identified by toxic dispersion modeling as toxic hazard areas, a description of any risk mitigation applied in the toxic risk assessment, and finally, a description of the population exposure input data used in according to 450.123. Next slide. In closing, as a summary of toxics or key concepts, the FAA would like to just share some takeaways. The operators are primarily responsible for determining use and identifying toxic propellants, conducting a toxic release hazard analysis, managing the risk of casualties that could be a result of any toxic exposure by hazard containment, and performing a toxic risk assessment. And finally, establishing flight commit criteria based on the results of its toxic release hazard analysis and toxic containment or toxic risk assessment necessary to ensure public safety. Next slide. So this concludes my portion of the presentation. Thank you for your attention. Please be reminded that the advisory circular for toxics is in the final stage of development and review. If you have any questions, please put them in the chat. And if there are questions come later, feel free to send those inquiries to the International Policy Group, John Sloan, and we can actually schedule technical interchange meetings with our system safety group or toxics MEs in the future. So that's all I have. Back over to you, John.
All right, thank you. I don't see any questions. We'll just give it a few more seconds in case we get something. As a reminder, we plan to send a message out later on where you can find the recordings from our 4 workshops. And I think we're done for today. Thanks everyone for attending, and I hope everyone has a good day.